Hello. In this lecture today, we are going to start coupled mode theory of guided modes. So, we have already discussed how to solve guided modes using full vectorial method, and then we also learned that how these guided modes are orthogonal, and we have derived also the orthogonality condition. Now, as long as those modes are orthogonal, they cannot exchange energy while propagating, co-propagating on counter propagating whatsoever. However, if you somehow break the orthogonality condition, then intentionally by your waveguide design or whatever you can, then there is a chance that these modes start, these eigenmodes start interacting each other. They can exchange power among themselves. So, for that purpose, we will be developing a coupled mode theory for a controlled perturbation, controlled breaking of orthogonality condition. So, towards that end, we would like to discuss first thing that we have to modify a bit our wave equations to convert it into a working model. So, what we will be doing? We will be working with dominant electric field component. So, you know there are there may be in principle hybrid mode, you can have three components for the electric field E x, E y, E z. Similarly, three components for the B x, H x, H y, H z. All these 6 components can be there, and T like mode, T m like mode, all those type of things are there. So, instead of handling all those components, we will be just concentrating more on the dominant electric field of the mode, and we would like to see how that dominant electric field, dominant component of the electric field evolved as there are some perturbations or waveguide structure changes, etc. For that purpose, we would like to learn first how to handle only the dominant electric field of the guided modes, how we can approximate that one. Then next thing is that we will just try to discuss mode couplings at waveguide junctions. That means, if you have two different type of waveguides, you can think of one waveguide with a certain cross section, another waveguide another cross section. So, if you are launching light in one waveguide, then what happens in the junction? Or if you have a waveguide, you are launching light from a fiber from the external source, and fiber you are just hitting exactly butt coupled to your waveguide, optical waveguide in a chip. So, in that case what happens? So, those things we will be learning first, that means coupling efficiency. That means, we would like to discuss about the coupling of one waveguide, coupling of the modes in one waveguide to the another waveguide having its own eigenmode solutions. Okay, that thing we will be learning, second thing. And then finally, we will be just discussing in this lecture the consequence of small perturbations in the waveguide. If there is no strong perturbation, then you can somehow little bit approximate your equations, and you can try to see what is the outcome, whether you can use it in a effective way or not, that I will be discussing. Okay. So, next thing. So, you know, as usual, this is our waveguide cross section. We are taking example of SOI, silicon on insulator platform. In this case particularly, that is a silicon rib waveguide structure, and waveguide parameters are W, capital H, small h, and h can be 0, and this one actually fixed by the wafer you are buying, and you can control W value, waveguide width. Okay. So, if h equal to small h equal to 0, then W and h waveguide dimension will be W by h. So, that would be like a photonic wire waveguide structure, and if you analyze the modes, then what you see, you can have most of the time you will be getting either T like mode or TM like mode. Let us consider only T like mode. In that case, you will have electric field in the xz plane, in the plane of the substrate, and magnetic field will be in the vertical plane, that is in the yz plane. Okay. And typically most of the time you will find that this Ex component is much higher than the Ez component, and here magnetic field Hy component will be also higher than the longitudinal component. Nevertheless, will be this transverse component Ex and Hy normally they contribute power propagation in z direction. That is why it is good enough to concentrate only on transverse components. And in case of TM, this will be changed, this electric field will be Ey and magnetic field will be Hx. So, these are the two components for the TM polarization you need to consider. So, let us start with a TE like mode. So, we can develop our theory for working theory, so that you can use them effectively. So, now, so as I mentioned that we need to only concentrate only on x component of the electric field for TE like mode. In that case, we know that the scalar wave equation associated with the vector wave equation, only Ex component if you use, you know that x component, this is x component Ex, and then you are using this refractive index profile. This refractive index profile is nothing but epsilon r equal to epsilon 0. We can write this one as something like this, n square x y. Okay. So, that way if we write, that is the refractive index profile we can write, and effective index of the guided mode, and then you have coupling equation. If this refractive index has a gradation in the xy plane, then we should have this term will be there. Otherwise, you can ignore that, assuming homogeneous core and cladding. So, this part I am just cancelling, and in that case I have very simple equation. We can consider this is a 2D waveguide for a homogeneous refractive index core and cladding. This is the equation, this equal to 0. So, only Ex is involved. Ex means that must be obviously that can be a function of x y, there it is mentioned. Okay. Right. So, now next thing is that since we are only concentrating only on x component Ex, we do not need to bother about what is Ez, what is Ey. Ey obviously in this case we are considering much less, 0, approximately 0 here we are considering electric field. So, we can keep in our mind that okay, this is the x component I am considering. Let us drop this x subscript, only you keep in mind that E is the x component, and it is a scalar equation. Of course, this is scalar equation, this is also scalar equation. Only whenever I am considering E now onward, we will be considering that it is a Ex for T polarization, and if it is for TM polarization, it should be considered as a Ey, nothing else. So, just T to TM, if I am dealing with the electric field, then I will be writing Ex here for T like mode, and it will be Ey like a TM like mode. Nevertheless, let us only concentrate E whatever the dominant electric field component, and it is just scalar equations. And of course, the waveguide cross section, we can just represent the waveguide cross section. The dielectric constant can be represented something like this. A is just symbolized as a waveguide cross section, somewhere core and cladding is there, and that is obviously what I mentioned earlier, that should be epsilon 0 n square x y. That is what we mentioned, same thing we are just repeating here. Okay. So far so good. So, let us move on. So, I have just written down this thing for using in following discussions. So, this is our scalar wave equations, where we have just multiplied omega square. In this equation, I forgot to mention that in this equation, this omega by c square I just multiplied here, and that will be c square. You can write 1 by c square is nothing but mu 0 epsilon 0, right. So, mu 0 epsilon 0 we can write here, in that case omega square mu 0, and I can write epsilon 0 times n square x y, that means your epsilon a. So, we are just writing dielectric constant directly, okay. And omega square by c square, and you know omega by c if you multiply here, omega by c n effective square, which is nothing but your beta, beta square. That is what it is written here. Good. So, that is what the scalar wave equation, and electric field is the dominant component, dominant electric field component as I put in the heading, and this is the dielectric profile, dielectric constant profile of the waveguide, which can be represented again in terms of refractive index profile. Okay. Now, if you have somehow mth guided mode, you know, if it is a waveguide, that can actually support a number of modes. Okay. So, you can represent mth mode. M can be, you can index like m equal to 0, 1, 2, 3 and so on. So, any arbitrary mode you are considering em, say x, y, z, t. Again we are just we can consider this as a scalar, that is a space dependent scalar, only we will be concentrating only the dominant field component. Then this is italics E m x y, that means I am just trying to express the mode field distribution in x y plane, that is with represented by this one, and phase part is this one. So, if it is m equal to 0, I will be writing a 0, e 0 and beta 0, that is it, difference. Okay. So, mth, if it is mth waveguide, mth guided mode if we are considering, and if you can replace this E as em, okay, then I get this equation. Okay. So, this em means basically it is nothing but em x y. Okay. Em x y, that means field distribution of the, of course, that is a dominant field component, dominant electric field component of the guided mode, mth guided mode, that is what em stand for here. Good. Now, next thing is that if it is a waveguide, now I am just trying to show you a 3D view of a photonic wire waveguide. So, this is your x direction, this is your, you can say this is a w, and this is a vertical direction, this is your h, capital H, photonic wire waveguide. I have just assumed h equal to 0. This is just for discussion purpose. And you are launching light from here, and you just want to see at a far distance, this is maybe z equal to 0, this is z equal to L and so on, and you are launching light. If you are launching mth mode at the input, mth mode is expressed like this, and obviously we can consider am as just kind of amplitude, and this is just a profile, electric field distribution profile, okay, in xy plane, and that will be propagating along z direction. So, that means the mode, if I just see what is the mode here in this cross section, as it propagates, it will propagate with keeping this type of shape fixed, and this type of phase as a travelling wave, it will be travelling all the way. That is why I can show there whatever the mode, mth mode I represent here, same mth mode will be represented also here. Only thing is that instead of beta m z, it will be just, you will be writing beta m L, and in this case beta m z, if it is z equal to 0, that part will be 0. So, it will be just a m e m x y e to the power j omega t, it will be there. So, that this one will be there, and here it will be a m e m x y, the shape will be same, and phase will be now at same instant of time. If I am considering, this will be beta m L, that is the difference. This will be input and that will be your output. If you are considering at time t instant, what is the situation, then this will be 0, this will be 1 and this will be 1, then you will be getting a m at t equal to 0 instant, I am talking x y, then you will be getting minus j beta m L. So, if you are taking a snapshot at t equal to 0, I can actually define what is the field strength at every point of z, I can define using this equation. This is a eigenmode solution that will travel carrying its own energy and power along the waveguide direction. We know how to calculate the power of a mth guided mode, right. So, now if you have instead of only one mth mode, if you have all modes, you can think of that m runs from 0 to, if it is supporting maybe 10 modes, okay, 0 to 10 modes, then what you have to do in at any point at z equal to 0, for example, we are considering what is the total field, you have to just consider sum of all fields at z equal to 0, you put z equal to 0 beta m. So, this is the sum, all modes I am just it is an electric field. So, anywhere if you have a multiple modes are propagating. So, at any point you want to see what is the total electric field, you have to see the superposition of all electric field along with its phase. That is why all individual mode they will have phase factor like this beta mz. If it is first mode it will be beta 0, second mode it will be beta 1, third mode beta 2, fourth mode beta 3 and so on. All these mode up to 10 modes will be there. So, you just see even profile will be E0 xy and then E1 xy, that profile will be different also, mode shape will be different and their amplitudes also can be different, we will discuss that. So, individual modes they can have different amplitude also, but at any point if you want to see what is the total field, you have to see the sum of all electric fields there along with its phase, because one field if it is just a phase is 0, another mode it is coming phase with opposite, that means exactly minus, then total field will be subtracted. So, that is how you have to just consider superposition of all field along with its sign or phase. Good. So, now the modes are normalized to 1 watt, that is what we have discussed earlier. You know the power in a mode we can calculate like this, half real part and then EM, if it is mth mode for example, EM cross HM star, and you have to see only z component, that means Az you have to see, and dx dy. Now, you know normally this electric field magnetic field, if electric field is in the x component and magnetic field will have only y component, assuming longitudinal component not contributing to the power flow in the z direction. So, in that case I can express that this is your Hy. Hy is this one, magnetic field is Hy and electric field along x direction, magnetic field along y direction. So, we can show from the Carl equation, we have shown in the previous lecture also that this Hy, so that will be beta by omega mu times Ex. So, it is just simple relationship. Okay. If you know the electric field distribution along x direction, then you can find magnetic field distribution along y direction. Okay. So, if you just substitute this one here, okay, then what you will be getting, ultimately you will be getting EM xy and EM xy star integration dx dy and then half real part, okay, and then obviously you have this beta by omega mu will be there, this beta by omega mu, that is the total power, right. Okay. So, if you are taking cross product, that cross product will give you that only Ex component and Hy component, and Hy component will be this one if you multiply, and we can find out that if this EMXY actually associated with amplitude AM, then I can write one amplitude will come here, another amplitude will come here, that is what AM square. So, we can write this way. So, beta by 2 omega mu, that can be taken to the right hand side. If this total power is 1 watt, that means I can write this one. Okay. So, if you are just using that just assumption that every mode, if it is mth mode, mth mode, if it is nth mode, nth mode, nth mode, if it is carrying 1 watt power, then I can write this, if this is the mth mode is represented like that, then this 1 watt expression can be written like this, 2 omega mu by beta m times 1 watt, because beta m by 2 omega mu should be this side when you are calculating your total power, that is actually 1 watt. So, you take that this side, then it is coming like that. Okay. So, now what you do? You have this expression equal to this expression. So, I can consider that this AM square actually equal to 1 watt and this one is equal to 2 omega mu by beta m. So, from this consideration that if every mode is carrying 1 watt, then the amplitude I can impose 1 watt, amplitude square can be imposed as a 1 watt, and whatever this expression is there, integration em, that means this one should be written like this, em xy square dx dy, that should be equal to mth mode 2 omega mu by beta m. So, that will be the expression. So, if you just multiply this one and this one, the am square, this one, then you will be getting 2 omega mu by beta m 1 watt, that is the expression you will be getting. Okay? Good. So, I have now another things. So, all these we are following from the orthogonality condition. Orthogonality condition, what is that? If these two modes are different, if it is m and this is n, then we can write here 2 omega mu by beta m times delta m n. So, if m not equal to n, that should be equal to 0 according to the orthogonality condition. If m equal to n, then this is the expression. We will be using this expression again and again when we will be developing our coupled mode theory. So, you should keep in mind. So, you should not only keep in mind this expression, you should know where from they are originated. So, this is the explanation. So far so good, we just repeated all the things so far we discussed: waveguide profile, dielectric constant profile, governing equation with a dominant electric field component. It can be Ex, it can be Ey, whichever is suitable. If it is T, it is Ex, for Tm it is Ey component, that is the dominant component. And if you are defining mth mode guided mode, out of many modes are there, you are just considering mth guided mode. So, this thing if you just put here, substitute here, the equation, it will be beta square will come as a beta m square, and whatever profile will be there, and you have to solve this one to find out em xy. To find out em xy, so you have to solve this equation, that is known. As long as epsilon a xy, this value is given, you know how to calculate numerically, the same methods you can use. And obviously, we have used that if the guided mode is defined by this one am em xy, that is the profile, and this is the phase part, then am square we have considered 1 watt, and this one we have considered 2 omega mu by beta m, that is in the previous slide where from they are coming. Just assumption is that you should keep in mind that okay, if I am putting am square equal to 1 watt, that means mth mode is carrying 1 watt. If you are putting m equal to 0, then fundamental mode is carrying 1 watt, m equal to 1, that means first order mode is carrying 1 watt, and so on. Good. Now, let us consider this thing. What we want to discuss? We wanted to discuss mode coupling at waveguide junction now. Suppose you have two waveguides, one waveguide here. Let us consider this is a single mode waveguide. This is obviously E is missing here, single mode waveguide. Okay. And in the single mode waveguide, you have only one mode is launched. This is A naught square prime E naught xy and propagation constant of this waveguide. So, this waveguide is characterized by this one, only one fundamental mode is supported here. Beta naught, you can write beta naught prime equal to omega by c n effective naught say prime. So, effective index of the fundamental mode, if you solve this waveguide, you can get this one. Okay. And E naught x y, it can be x component or y component depending on the TE and TM polarization, that also you know. Suppose this is known, and obviously you can consider this thing A naught square equal to 1 watt normalization you can consider. Now, this single mode waveguide is connected to with a little bit wider waveguide structure. So, suppose this is W naught here, and this is just modified the width only, just width varied, vertical direction you have not changed. So, what happens here, you can have many modes, okay? It is multi-mode waveguide. So, if you just think of that, what is the total field E out, if you are considering x, y, z and t. Okay. At any point, if you want to know what is the electric field output in this output waveguide, this is the multi-mode waveguide junction here, then I can say that all the modes are there, their amplitude is AM, A0, A1, A2 and so on, and their field distribution is this one and corresponding phase is this one, superposition of them at any coordinate at any instant of time you can find. Now, thing is that these are the solutions here and this is the solution here. Now, all the solutions there does not mean all of them are active. You can actually selectively choose to excite a certain mode. Suppose if it is m equal to 0 to 10 modes are there is you should have your own choice to excite maybe 5th mode or 4th mode or maybe all the modes or none. So, how that is being decided? What happens? Suppose I have a waveguide, input waveguide, where I have only fundamental mode we are launching here. At the junction it is open wide, it is a wider waveguide and I have all possible solutions m equal to 0 to 10 solutions are there, guided mode solutions, and I am considering that no other losses are happening here, for example in the junction. So, whatever power carried by this mode, that should be actually transferred to the multimode waveguide region, but I would like to know which mode will accept how much power. Suppose it is carrying 1 watt. Does it mean that this 1 watt power will be distributed equally to all modes if it is coming here at the junction, or it will be completely coupled only to fundamental mode, other modes will not be excited? So, that is the question now we have to discuss. So, let us proceed how we can deal that. Okay. Now, you see, if I just put z equal to 0, this is z equal to 0 I am considering, this position is z equal to 0. At z equal to 0, that means I can get what is z equal to 0 here, this is actually a naught is equal to 1 you can consider, of course, a naught equal to 1 prime and E naught x y e to the power j omega t. This is here. What is the field you will be getting here? E naught prime x y e to the power j omega t. And from this one, what you will be getting here? E output at z equal to 0, I will be getting E out. Okay. E output will be equal to A m all the things and E m x y times e to the power j omega t. So, e to the power j omega t, e to the power j omega t, if you cancel at z equal to 0, I am just considering like this. So, I am assuming that all the power is somewhat is going into the second waveguide. That means, whatever amplitude here, whatever the field here, that can be considered superposition of all these modes at z equal to 0. Whatever the modes are there, you can consider superposition of all modes will produce this mode. That is what mathematically we can express this one. So, this is the mth mode field distribution, mth mode amplitude, and if you are adding all these mth mode field distribution and their amplitude, that should produce the input mode profile. If you are considering this A naught equal to 1, that means 1 watt power is launched in the input waveguides, right. So, I can easily write at z equal to 0, this is the expression. Okay. And obviously, since I have assumed that no other losses is there, all the power coming in that is going into the multimode waveguide, I can consider individual mode. Suppose how much power will be there in the first mode, this will be A naught square, and what would be in the second mode, that is A 1 square, third mode A 2 square, fourth mode A 3 square. So, all these if you sum up, all the power you sum up, that should be equal to 1 watt, because you are launching at the input 1 watt. That is why we are writing A m square, all the coefficients square if you add, this is we can consider coefficient of the mth mode, and if you are taking square, then you can get that would be equal to 1. Okay, fine. So, now with this I have just written this one here, and this is that z equal to 0. Now, what we do with this? What I will do, let me try, I just multiply E n star x y this side, E n star x y this side. So, E 1 star x y, both side I am multiplying, and after multiplication I just integrate over x y cross section, that is the left hand side. I multiply E n star x y and I am integrating over dx dy. Okay. Just simply I am just En is the En star xy means that is the field distribution of the nth mode of the multimode waveguide section. That is what I am multiplying in both sides. So, if you multiply this side En star, right hand side also I multiplied En star Em this one. So, simply multiplication and integration both side. Am is there. Now, let us concentrate this one. It is actually first thing is that I will be considering Em xy, right, or E1 and En star xy dx dy, that is the first one I consider A1, and second one it will be A2 and E2, that is plus xy En star xy dx dy, and third term A3 and so on. So, all these terms you have will be adding, but what is the n? En star, that is the nth complex conjugate of the nth mode, and this is the first mode. So, we know that according to the orthogonality condition, if m not equal to n, that means this value and this value unequal, then their overlap integral that should be equal to 0. That is what we learned from orthogonality condition. So, these all these terms, some term, they will be vanishing, but when m equal to n, that particular term will be surviving in the right hand side. So, we simplify that one, that if it is so, only that part will be surviving, that right hand side will be Am Em xy and En star xy, En will be become Em dx xy dx dy. So, right hand side will be reduced to only one term. When m equal to be applying just orthogonality condition, when m equal to n, that term will be surviving, all other terms will be 0 because of the orthogonality condition. And then if it is so, then this is Am, that will be equal to your left hand side is this one. So, if I just equate these two, what will happen? I can find out what is the value of Am. So, Am equal to this one divided by this one I have written here. This one means Em xy star, so square it is written. So, I can find out Am. That means, if I know how much power is coming, this expression I know the field profile I can calculate easily, okay, and of the multimode region as well as single mode region. And if I know, if I am launching fundamental mode, then how much fraction of power will be coupled to the mth mode, that is decided by the Am, because A naught square is a 1 watt here, and A 1 square, for example, if A 0 square you are considering, that is the fraction of power, it will be coupled to the fundamental mode. When A 1 square, that is the fraction of power will be coupled to the first order mode, and so on. So, we know that this expression, if we can evaluate mathematically, numerically, then we know how much power will be coupled to the different modes depending on this m value. M value according to the field profile you have to write. So, that is this thing again we have derived that this one is nothing but normally we have discussed earlier, right. That is actually if you are integrating Em xy En star xy dx dy applying the orthogonality condition and 1 watt power, this is actually 2 omega mu by beta m. Okay. When m equal to n, that will be surviving, otherwise it is delta mn. M not equal to n, that will become 0, m equal to n, that will become 1, that is the Kronecker delta function, right. So, if I use this denominator, this concept, that Em multiplied by Em star, that means it will be 2 omega mu by beta m, that means Am can be written as beta m by 2 omega mu. So, this is the thing. So, only thing is that I need to know what is this. This was the field distribution of the input mode here E naught prime, and this is what? This is the field distribution of the mth mode, and you are integrating over xy cross section. So, that means if you know what is the overlap of the field distribution, This is actually we called it as a overlap integral. Overlap integral. So, if we know the overlap integral, how much overlapping you have to integrate, you have to multiply every coordinate in the cross section, and then you have to integrate, you have to add all of those, and then if you multiply beta to omega by mu, then whatever value you will be getting, if you just square it, that is the fraction of power, that is the amount of power you can get. Suppose you are 1 watt you are getting here, if this value it is coming like that, say 0.5, that means for m equal to 0, that means I can say that 500 milliwatt power is coupled to the fundamental mode, and I can individually I can calculate. So, this is what very important information about how modes can be coupled, how you can excite a particular mode. For example, it can happen that, so for example, light coming from here from a fiber, for example, fiber is a core like this, and here fiber is there. So, core and cladding is there. So, light is coming here along the fiber. So, you know what is the field distribution of the fiber, right. So, you can just express that EF x y, that is the field distribution of the fiber mode. Then if I want to calculate how much power will be coupled to this fundamental mode, then I can easily say that that is actually proportional to EF fiber mode field distribution times E naught prime x y dx dy. So, better overlap between these two mode, you can have better coupling. Okay. If these modes are actually exactly matching, then your overlap will be 1, because this field, if this field is matching exactly, then this value will become 2 omega mu by beta, right, something like that, same. If they are identical, then 2 omega mu by beta and this beta m by 2 omega mu, they will cancel, then you will be getting 1. So, if you want to couple light from one waveguide to another waveguide, first thing you should ensure that their mode should be matched, their overlap should be equal, unity, sorry, overlap should be unity. So, if their mode field distributions are different, then you will not get overlap integral unity, and your coupling efficiency will be less. So, any two fiber, their field, you have to see what is their field distribution. Waveguide can be different configuration, core can be different, cladding can be different for the input waveguide, core of the output waveguide and cladding of the output waveguide can be different, but you have to see if their modes are, field distributions are equal and their overlap is coming almost is unity, then you can say that maximum power transfer can take place. Of course, you are actually ignoring if there is any impedance mismatch happening or not. Mode matching is happening, impedance matching means effective index of the input waveguide and effective index of the output waveguide, they should also match. Then only you can say that there is no Fresnel reflection back to the input waveguide or input side. So, two things you have to concentrate in coupling from one waveguide to another waveguide, or maybe input fiber to output waveguide. Okay. So, one thing is that effective index should be matched, that is the first condition, and then mode field distribution, field, if it is electric field distribution should be exactly equal to the electric field distribution of the output waveguide, then maximum power transfer will take place. As it go away, if they are mismatching, then your coupling efficiency will be dropping according to the how much fraction it is overlap you are getting. Okay. So, here also you can think of, suppose you can consider here in this waveguide, suppose you are considering a first order mode like this field distribution, and fundamental mode will be like this in the center. So, if you take the overlap, first half you will be getting positive and second half if you integrate it will be negative. So, it is sure that if your input waveguide is exactly positioned in the center and your output waveguide is just going out here like that, then you can say that this first order mode where your one half is plus, another half is negative, overlap will be 0. So, that mode will not be excited because overlap integral will be 0. So, in that case what you have to do, you have to position this waveguide little bit off centric, then you can get certain overlap also, then there is a chance that the first order mode will be excited. So, it depends on input waveguide positioning and output waveguide positioning with respect to that. Depending on that, you can actually control which mode you want to excite. If you want to excite all the modes, accordingly you have to just set that overlap integral for the all modes should be non-zero, and you can find whatever the coupling efficiency. This is very important for integrated photonic applications. Okay. Now, I know that effective index here n effective not 1 and effective index here is n effective not, for example, and n effective 1, n effective 2, n effective 3, so on. I know that how much power will be coupling here by calculating overlap integral, but if I know n effective is this one, how much power will be coupled to the first mode and how much it will be reflected back to the first mode there. Then you have to see the effective index mismatch of the fundamental mode to fundamental mode, how much, that you have to see, and you have to use your Fresnel reflection condition, like reflection coefficient. You know that reflection coefficient is n2 minus n1 by n2 plus n1 for normal incidence, theta 1 equal to 0, we have learnt when we are discussing about plane waves and so on. So, that thing will happen, that some kind of reflection will be there, okay. And after reflection whatever coming in, suppose 1 watt coming and then maybe 0.1 milliwatt is reflected totally because of the Fresnel reflection, then 0.9 watt will be distributed among the output waveguide modes, and among 0.9 watt they will be again can be calculated depending on their overlap integral. So, that is the idea. But can we do something so that I have a single mode here, I am launching here, and here I have many modes. I do not want to lose any power, but I want to couple all the power from the input to the output waveguide, but not to the all modes. I want to excite only one fundamental mode. How that is possible? So, that is actually very much possible. So, how that is possible? You have an input waveguide here, okay, and input waveguide, the field distribution you can express like this. This is the beta naught prime is the propagation constant, that is you are solving for the input waveguide, and this is the field distribution, and this is a naught square, a naught prime, you can always consider that is 1 watt, okay, and all the orthogonality condition you can think of. Then you have, this is the waveguide where you have multiple modes are there excited, but this is the fundamental mode. What I want to do? I want to convert this entire power into this one, so that approximately a naught prime square approximately should be equal to a naught square. How that is possible? So, you do one thing, you instead of just abrupt junction, waveguide junction, you do slowly tapering the waveguide, width you vary slowly, you allow some length, L taper length, okay, some length you allow, and slowly you increase and merge into this waveguide. So, that what happens, every point, if you, every cross section if you see here and every cross section if you see here, okay. So, nearby cross section if you see, waveguide dimension is not suddenly changing, slightly delta amount it is increased, delta amount effective index is increased. So, in that case you can consider this mode when it is going from one position to another position along z axis, for example, then it does not see abrupt change of effective index. So, in that case you will see loss, Fresnel reflection loss will be minimum. From, you can just consider local normal modes you can solve, and you can check that effective index difference is not that great. So, reflection will not be that great, that high. So, you can actually slowly you can see this E naught prime also will be evolved little bit bigger, and effective index also will be little bit increased slowly. And if you just keep on going further, as it propagates, you will see that they are actually changing, they are increasing the field diameter, the distribution area, that will be increasing also slowly, and effective index also will be increasing slowly. Obviously, you know this beta naught, because wider waveguide, beta naught is higher than beta naught prime, okay. So, slowly it will be increasing. So, as it propagates, if you just allow them to slowly evolve, then it is possible to achieve this type of power coupling, and you can achieve only to couple to the fundamental mode only, even though this waveguide can support many modes. Okay. So, that is called adiabatic tapering, and practically people actually demonstrated such a adiabatic taper in silicon platform, and insertion loss can be much lower than 0.1 dB, almost no loss, but this taper length actually that depends how fast you are tapering. If it is faster tapering, if this length is small, then it will be lossy. You should allow sufficient length so that it can evolve slowly and to take a shape of the fundamental mode of the multimode waveguide. Okay. So, that is one useful technique when you are making different type of waveguide and you want to transfer power from one particular device to another particular device of different dimension. For example, waveguide dimension can be different. You can couple the entire light with less loss, less insertion loss. That is called, that is why, since it is no loss, no energy is being lost, ideally I would say, then it will be calling as a, that is why it is called as a adiabatic taper. Adiabatically it is mode is converting from smaller size to bigger size. So, that is sometimes it is adiabatic taper, and sometimes it is also called as a spot size converter, SSC. Sometimes it is called spot size converter and sometimes it is called mode size converter. So, in literature textbook they define differently, but it is basically the same, mode size converter or spot size converter. Okay. Good. Next thing is that suppose you have a as I mentioned here, this is a nice thing, that we found that if you are slowly increasing your waveguide width, that means your dielectric constant or waveguide dimension or effective index is slowly increasing. In fact, your mode shape can remain same and your fundamental mode is evolved into fundamental mode in the multimode waveguide. Even though higher order modes are there, they will not be excited. That is a beautiful thing. So, let us see if somewhere in your waveguide you have your some kind of perturbation. You know, this input waveguide is defined by epsilon a x y like this, and output side also it is defined like that. A certain region from z equal to z naught to z equal to z naught plus L, this region you have some kind of small perturbation. What is the consequence of small perturbation in the waveguide? So, if you have a very small perturbation, maybe this width may be little bit high low or something like that happening, or height of the waveguide may be changing high low, or maybe some kind of roughness is there, some kind of edge roughness is there in the waveguide, that can be considered as a perturbation. That means the dielectric constant is delta epsilon is changing. Or you can think that, you know, any waveguide, if you have here waveguide mode is like that, if you somehow, if you have some another waveguide also coming nearby, suppose another waveguide also coming nearby like this, okay. Suppose this is another waveguide coming side by side. So, what that means, this waveguide, if there is a evanescent field, this mode solutions you get here, right, this mode will see outside instead of air. After certain time it sees the tail to second waveguide it can see. This second waveguide can be considered as a delta epsilon for the first waveguide, and vice versa. If you are considering this waveguide, presence of the other waveguide, you can consider this mode here, guiding mode here, it will see some kind of disturbance, some kind of fringing effect for the neighboring waveguide. That type of perturbation if it is there. If these two waveguides are far away, then no problem, because the evanescent field it will be quickly, it will be reduced to almost 0 before the second waveguide comes in. But if these two waveguides comes closer, you can see that okay, they are actually disturbing each other. Okay. That disturbance I can consider as a this waveguide with perturbation of this one. Okay. So, in general I want to discuss first, if this delta epsilon is there, some kind of perturbation, this can be presence of second waveguide neighboring second waveguide, this can be some kind of intentional waveguide width variations, or maybe it can be intentional periodic perturbation, some kind of grating structure you are making, or it can be that grating structure you can make some kind of corrugation, surface corrugation or etching, some kind of periodic etching, etc. you can do. So, those type of perturbation if it is there, what could be the consequence, what would be the outcome of this result? You know, for example, if it is just perfect waveguide, homogeneous waveguide, you can see number of modes can be guiding, and superposition of all those modes I can write like this. Of course, we are so far we are discussing it in the Fourier domain, frequency domain, only one frequency monochromatic. So, one frequency we are considering. If another frequency, you can just treat them with another frequency. Otherwise, sometimes you can directly solve your Maxwell's equation using your so called FDTD technique, finite difference time domain technique. We are just considering frequency domain, it is easier to understand all this coupled mode theory, etc. So, here in the input side, I know that this is the all the modes and field at any point, that can be superposition of all the modes. And in the output side also I can consider the mode, because there is no perturbation here, it is as good as input side. This is your input waveguide side and this is your output waveguide side. So, they are identical, but thing is that in between you had a perturbation, something has happened something in between. So, in the output side also you can see similar type of modes at the output, they will be propagating, but only thing is that because of the perturbation maybe this AM is slightly changed. That means, there might be this perturbation region, there might have happened that all the modes they exchange somehow some power, because you have already broken the orthogonality condition there. Because as long as your waveguide cross section is maintained, then your orthogonality condition is not broken, and that is why you have all the modes propagating like a independent way individually. Okay. So, that thing if it is happened, what would be the consequence, how you could actually change, modify your equation, that is what we are going to discuss. Let us see. So, here you see governing equation, I can just simply write the same equation here, this equation I have written here, that equation here, and for this side also I can use this equation here, omega square mu a, that is directly coming from the scalar wave equation. Okay. Now, how to define here this region? If you have a small perturbation, you have broken the orthogonality condition, but not abruptly, it is a small perturbation. So, if that small perturbation, then what type of equation should be involved here? Can we modify these equations so that I can get a certain approximate model here, so that I can actually find, because of the magnitude of the delta epsilon, the randomness of the delta epsilon, we can say that how the outcome results that can be calculated. Okay. So, let us see. What we can say that since you are breaking the orthogonality condition here, can we write like this? What is that you see? What is the difference between this to this? Here AM is constant, as it propagates individual modes will carry same power, same energy, same amplitude. But here because of this perturbation, what I consider that as it propagates, mth mode will see some kind of variation in amplitude along the z direction, because amplitude actually because of the perturbation you see certain kind of power exchange, orthogonality condition broken. However, we can say that if delta epsilon is very small, if it is small, then we can say that this mode field distribution is not changing much. If you solve the mode field, electric field distribution from the vector wave equation, etc., that is not going to be changed, because delta epsilon, this dielectric constant or waveguide width or whatever change is that is very small. So, I can maintain that field distribution exactly, and I can also say that individual mode will not see much change in a propagation constant. So, that this is approximation, you know, just to use Maxwell's equations, all the scalar wave equation to develop a working model for waveguide and integrated optics, you need some kind of approximation. So, that is what engineering is called. Okay. So, we are just considering this approximation. This is just approximation, as long as this approximation is good, your device is good and you can use for experimental demonstration or practical device applications. Okay. So, we can consider this one. Then if we just consider this one, can we use this equation directly? Obviously not, because your this epsilon A xy is now converted into this one. So, you need to insert this one here. Electric field you can insert here and this one you can insert here. So, once you insert here, that will be the new equation. So, you are just converting epsilon plus epsilon A. But by the time what we have done, since I am using this total electric field, Z dependence things is there, because this beta square comes because of the del Z equal to minus j beta, and del Z2 equal to minus plus minus beta square. Okay. So, if that beta square you are writing here, minus j beta square you are writing, that is why del ZT was not there here. But if I just use Z dependent function inside the electric field, then I can just write down del Z2, this one I have included, and beta square not given there. So, now what we have to do? We have to solve this equation by substituting this here. This electric field I will be substituting here, and I will try to solve what is the evolution of this individual mode amplitude. So, if I insert here and try to solve for AMZ, then I am done. I will be able to know as a function of Z what is the situation or power of mth mode. So, that is one major thing we can say, that just controlling that particular delta epsilon we can control this AMZ value, and that can be a very good successful device application we can think we will see also in course of time. So, we would like to develop this type of model. I will be considering in the perturbed region the field of individual mode that can have some kind of evolution. Z dependent variations will be there, that is actually represented by this amplitude. Amplitude is going to change, okay, as a function of Z because of this delta epsilon. As long as this delta epsilon is there, so this AM keep on changing, evolving. Okay. Now, next thing. So, now next question is that in that case I need to know what is the value of AM. All the modes are there, AM at Z equal to 0, what is the value? Obviously, whatever you are launching here, that would be the AM Z equal to 0, right. At Z equal to 0, whatever the value is there, you can just consider that one from the input side, whatever coming, right, for that particular mode. Whatever the excitation will be there, that we can find out. Okay. And then what will happen? What about AMZ? AMZ equal to L. At L, whatever the amplitude will be there. That means, after that I have again smooth waveguide, no perturbation, nothing. It will be propagating like that, right. So, in that case, I would like to find out what is that value. If we know that, then I can say that because of the perturbation, how much I lost, what is the survival of individual modes, how much fraction it is surviving. Okay. So, next thing is that will there be any backward propagating waves? So, everywhere if you see, we are considering forward propagating wave, but because of the perturbation you can consider some kind of scattering points, right. But macroscopically we are trying to get a model like it is all are forward propagating wave, and we have used Maxwell's equations, etc. But because perturbation means some kind of dielectric perturbation, right. Dielectric perturbation means you can think of Fresnel reflection, refraction, scattering, everything will be there. That scattering can cause anything constructively towards backward direction or not. Will that be will there be any power reflected backward direction and can take up some mode shape and propagate in the backward direction? If so, how you can actually control that? That is the thing we need to discuss in the next lecture. That means, we will be trying to develop a coupled equations, controlled coupled equations, so that we can use them for various applications. Thank you very much.